In this video, we're going to talk about the equilibrium constant, specifically the effect of differing conditions on that position of equilibrium in reference to Kc. Now, in equilibrium, we can just describe the position of equilibrium by when the concentrations are the same. So you can see up here, we've got concentration in moles per decimeter cubed, and then we've got time. If I just walk over here, this is for the Haber process. So NH3 is the red, H2 is the orange, and N2 is the yellow. So basically you can see the reactants are coming down, makes sense. So the reactants start with a really high concentration, they come down, and then the product goes from low concentration and then comes up. And then you get to a point, which is around about here with our equilibrium. And you can see through that equation, all of these are staying at the same concentration. So the concentration is staying the same. Now that is our position of equilibrium because the concentration does not change because the forward and backward rates are exactly the same. Now, just going into this in a little bit detail, remember that definition, forward and backwards reactions are at the same rate in a closed system, green because you need it, okay? And we can go through different types. So we know we can do homogeneous equilibria, where all of these reactants and products are in the same state, and we know we can do heterogeneous equilibria, where we have different states. Just to remind you again of Le Chatelier's principle. So Le Chatelier's principle is just basically if there's a change applied to a system, you will oppose the change. So higher concentration is imposed, system will want to lower the concentration, usually by reaction. If a higher pressure is imposed, it will lower the pressure by going to the side with the lowest moles. But again, we'll explain that later. And a higher temperature is imposed, the system will lower the temperature by following the endothermic reaction. Again, we'll explain that in more detail. But this is Le Chatelier's principle. Again, don't need to remember Le Chatelier's principle, you need to understand. So in essence, you do really need to remember it, but not word for word. Now, if that is the case, let's have a look at the effect of concentration on equilibrium and try and put it into a more of a picture type format. So here you have 4 particles on the left, which is your A in the red, and 2 particles on the right, which is your B, which is your product. Okay, so the concentration and the position of equilibrium, okay, means you will have a higher frequency of collisions with the side with the more particles. So if you see here, there's more particles here, so there's more chance of them colliding. Higher frequency means they'll have a higher rate going in that direction. Okay, so if that's the case, this has got a higher amount of particles or higher moles per decimeter cubed, so there's going to be more reactions. So this particle is going to go over to the side. And then to put it in simple terms, you can see here there's the same amount of particles either side in this example, and therefore you'll get the rate going the same forward and backwards. So the equilibrium will move to the right, as it did, move to the right, again, as the reactants have a higher concentration. So that also means you can do it in a different way. So imagine you've got a continuous process where A is being turned into B, or for example, nitrogen and hydrogen are turning into ammonia. If you had a system, usually through distillation, where you can remove the product, that means you're lowering the concentration of the product, which means the opposite really of that is that you're highering the concentration of the reactants relatively because you're lowering the concentration. And that is one of the ways where they keep a reaction going, is they remove the product as it's made, which relatively speaking means there'll be a higher frequency of collisions in your reactants, which means the equilibrium will always go to the right, which means you'll get a higher yield. Okay, so one way of increasing the concentration of your product is just to increase the concentration of your reactions. Higher rate of reaction, equilibrium goes to the right. Okay, and if this is in the exam, the really important thing is the bits in orange. Equilibrium is going to the right, you'll have a higher yield. The explanation really in terms of the frequency collisions in your second year of A-levels is not so important. We're now going to talk about the effect of pressure on the position of equilibrium, and we've got a reaction here, 2A going to B, this reversible reaction here. Now, imagine that you started off with 4 particles of A and 2 particles of B. So my B is my blue and my A is my red particles. And we're going to shorten this down a little bit and say, well, let's imagine these as a mole each. So we could actually say that this is 4 moles in here and 2 moles in here. Now, obviously this would be in the same container, but for simplicity, we're going to say if it was just A, it would look like this, and if it was just B, it would look like this. And we've just chosen an amount of particles in the ratio in the equation. So the stoichiometry of the equation is 2 to 1. So we've got 4 here and 2 here, so it's a 2 to 1 ratio. Now, if we just had A, this would be higher pressure because there are more particles in the same size container. If we just had B, it would be a lower pressure because there'd be less particles in the container. Now, how does this affect the pressure and the position of equilibrium? Now, if we increase the pressure, and we're going to do this now, imagine these are 1 decimeter containers. And like I say, imagine each one of those is a mole. So we've got 4 moles in 1 decimeter. And then we've got here 2 moles in 1 decimeter. We then increase the pressure, as in the question here, and we do that by reducing the size of the container. We can also add more particles in, but we're going to reduce the size of the container. Now it's now half a decimeter. So now think about it. What's the concentration here? The concentration is now 4 moles in half a decimeter, so it'll be 8 moles in a full decimeter. It's now 2 moles in half a decimeter, which would be 4 moles in a full decimeter. Okay, so the side, and we can still see here that the side with the most moles, as in the stoichiometry in the equation, will have the highest pressure if the equilibrium goes to that side and we just produce A. Okay, so this is your higher pressure side and this is your lower pressure side. So if I want to lower the pressure, I want to go towards the right. If I want to higher the pressure, I want to go towards the left. So if I want to lower the pressure, the rate of reaction is going to increase that way. And if I want to higher the pressure, the rate of reaction is going to increase that way. Now, why does that actually work? Okay, so if I increase the pressure, the system's going to want to do the opposite because of Le Chatelier's principle. The opposite of that is decreasing the pressure. So it's going to go towards the right. But why does it go towards the right? Well, as you can see here, the increase is 4 to 8 and the increase is 2 to 4. That means because there's more moles on this side, there's a much larger increase in concentration here. And if there's a larger increase in concentration, there is a higher frequency of collisions. So this higher frequency of collisions then goes in that direction. Okay, will make more of your product, B. Now, that's the explanation as to why it works. And if I, for example, lowered the pressure, okay, it would work in the same way, but in the opposite, so lower pressure, then go to the higher pressure side. Now, if we increase the pressure, side with most moles would increase and its concentration would have a higher frequency of collisions, but the really important thing is the equilibrium will move towards the right, and that's the side with the least moles. And if, for example, you decrease the pressure, the equilibrium would move to the left in this case, would be the side with the most moles, okay, and increase that pressure. We're now going to look at the effect of temperature on equilibrium. We've got a reaction here, 2A going to 3B. So first of all, the stoichiometry, 2 to 3 doesn't really matter that much. But what we've got here is an endothermic reaction. You can see here it's highlighted, so it's positive. And what that means is as you go in this direction, it's going to take energy in from the surroundings. And it's deliberately in blue because it's going to get colder. So it takes that energy in, takes 83 kilojoules per mole from the surroundings, and the surroundings then get colder. I always think about it in terms of Harry Potter, when you've got the Dementors will come in and suck the soul. So if you suck the life out of a room, it's going to get colder. Okay, so if this reaction is sucking that energy out of the room, so the energy gets nice and cold. So if that is the case, we have got these cold particles here, which is in blue, and then if we go in the other direction and we go back to A, we're going to get hot. Okay, so if we increase the temperature from this point, okay, now already it's very hot on that side, so you've got A, right, but you've got B on the other side. So this is the higher temperature side, and the other one, the B, is the lower temperature side. So if I go in that direction, I'm going to lower the temperature. If I go in this direction, I'm going to higher. So it says, what if we increase the temperature? Well, remember, Le Chatelier says you do the opposite. So if we apply an increase in temperature, then the system will want to decrease this temperature. The only way it can decrease the temperature is if it goes in the forward direction, because it's going to lower the temperature there. Okay, so the opposite of highering is lowering, and you can only lower by going the endothermic direction. If it was the other way around and this was an exothermic reaction, okay, what happens if it was an exothermic and I increase the temperature? Well, it would go in the endothermic direction, which in that case would be backwards. Well, let's go back to this one. So it's endothermic in the forward direction. Okay, so if we increase the temperature, it would increase the rate of reaction of the endothermic direction, which is that one, in the forward direction. Equilibrium will move to the right. The really important things you write are it follows the endothermic direction and it goes to the right, which will eventually make your yield of product go up. Our last condition is going to be talking about the effect of catalysts on equilibrium. Now, the most famous one is going to be the Haber process, so nitrogen, hydrogen going to ammonia. We've got minus 63 as our overall enthalpy change, but that's not really important when it comes to the catalyst. The catalyst, remember, just increases the rate of reaction by following an alternate pathway, and that's it really. It just increases that rate of reaction going forward, but what it also does is increase it going backwards. So basically it increases the forward and increases the backwards. Now, if that is the case, if you increase the rate of the forward and backward reactions, you get no change overall in the equilibrium position. You'll still get the same concentrations reached. And remember, when it comes to equilibrium, we say equilibrium position goes to the right or the left, right? Whether the rate of the forward is going faster or the rate of the backward. But remember, both of those are speeding up at the same rate. So basically, same equilibrium position. Now, that means, though, that the equilibrium is reached faster. So catalysts are really, really good because you don't have to wait days for your equilibrium to be reached. You don't have to wait hours. It can be done very, 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 very quickly. Now, this is an interesting proposal because if you think about this, and what I'd like you to do now is separately just look at this equation and try and figure out what are the best conditions for this high pressure, low pressure, low pressure, low pressure, for example, or high temperature, low temperature, or what would be the best way to get this thing actually working properly? Now, you don't often get asked questions in it, but sometimes you can get questions that lean to this. So have a think about what the best conditions are for this reaction. So hopefully you had a chance to think of your conditions. We're going to talk through it in a bit of detail here because we're going to talk about this equilibrium compromise as well, which might come up in your exams. Okay, so what we have, Haber process is the most common example, so we'll use that. So first of all, we need to look at here and go, how many moles have we got? So we've got 4 moles on that side. So you see this and this. We've got 2 on this side. So basically we are going to go 2 moles. Right, so we've got our 2 moles. And then we need to say, right, okay, which one's going to be the high pressure, low pressure side? Because you know our number of moles. Well, 4 is more particles than 2. So this is going to be our high pressure. Okay, so that's our high pressure side. And then that means this will be our low pressure side. Okay. We can then look at the equation here. So we say, right, minus 63. So it's exothermic in the forward direction. So so if that's exothermic in the forward direction, it's going to get hotter as you make this because the energy is given out to the surroundings. So basically, we'll just write that in a different colour. And then basically this is going to go hotter. Okay, and if that is the case, and that is going to go hotter, then the other one is going to go colder. Okay, so colder. So we've got colder and we've got hotter, right, good. Now, if that's the case, now we can go from here and say, right, what do we want in terms of pressure? So we want a high yield, we want the equilibrium to go to the right. So what pressure setting do we want? So the pressure setting basically is I want to get more of this, which means I want to move to the low pressure side. So the opposite of the low pressure side is higher pressure. So if I apply a higher pressure, Le Chatelier's principle said it's going to want to do the opposite and go to the low pressure side with the least moles. So basically my conditions for getting the highest yield is going to be a higher pressure. Okay, so it's going to be a higher pressure. And that's because it's going to the side, and it's going to the side with the least moles. Okay, and that's your exam answer, going to the side of the least moles. High pressure, which means it moves to the lower pressure side, which goes to the side of least moles, which is the right side, which is your yield, high yield, and which is your high amount of product. Right, if we then go to our temperature, okay, so we have our temperature, and we look at the exothermic, we want to go to the product side, we want to get lots of yield, okay, so we want to get hotter. We want it to get hotter. All right, so if we apply a low temperature, it's going to want to do the opposite and get hotter, which means it will go to the right-hand side. So this means we have a lower temperature. Okay. Right, if we have a low temperature, it's going to follow the exothermic direction. Again, this gets our full marks in our exams. Okay. Right, so we've got that. So we've got two conditions. All right, now what this will do, which means the equilibrium. Okay, there we go, the equilibrium. Okay, and that equilibrium will go to the right, which means you'll get a high yield. Okay, so perfect, right, that would be how I do the reaction. Now here's the compromise. So the compromise is this, the actual conditions for this are around 450 degrees Celsius, okay, and they are 200 atmospheres. Now, that doesn't really mean anything, they're just numbers, okay? So, but what if I turned that around and said, that is a relatively high temp, and that is a relatively low pressure. I say relatively, it's still 200 times the pressure at atmosphere, okay? So if that's a low pressure, that's a high temperature, okay? That high temperature is the opposite to our low temperature, that low pressure is the opposite to our low pressure is opposite to our higher pressure. So they're opposites. So I'm going to try and explain how this works. A lot of information on this board, so let's pull this all together. I'll give you an example. So let's say these are conditions number 1, and these are conditions number 2. So these are the actual, and these are one of the conditions to get the highest yield, okay? So if we go for number 1, and we're going to do a really simple comparison here, really simple. Let's just say we go for 1, we're going to get a high yield. Let's just say we get 90% yield. And let's keep it really simple and say 90% yield is going to end up in 90 kilos, just to keep the numbers really simple. And then we're going to go for number 2. So number 2 is the actual conditions. And the actual conditions, again, just keeping it really, really simple, is a 10% yield. So you can see that between these conditions give you a high yield. There we go, good, 90%. And then the conditions over there, the real conditions, are going to give you this lower yield, right? So, again, keeping it really simple, so that gives me 10 kilos. Because this is all about money. This is all about money that businesses make and all this kind of stuff. So if that is 10 kilos, right. But what I haven't told you is this. First of all, I haven't told you how long it takes. Because the reaction takes a length of time. So if I look at this and just say, right, okay, I'm at a low temperature, okay, and I'm at a higher pressure, admittedly, but I'm at a low temperature, which means my rate's going to go down, right? Which means that I'm going to make 90 kilos, but it might make me 24 hours of this turning around inside a big pot, or kind of all hitting each other within this big reactor vessel. All right? So if I then take this and say, right, okay, I'm going to higher that temperature, so I've got 450 degrees versus this low temperature that I would want to normally have to get that high yield. Okay, and I get this, and again, this is just a simple representation, and I get it in 1 hour. Okay, so I'd only get 10 kilos, but I get them in 1 hour. Okay, and that's because I get it in 1 hour because higher temperature, okay, which is a higher rate. Okay, because rate and position of equilibrium are two different things. The reaction can go very, very quickly, but get a low yield because the equilibrium is more to the left, or it can go very slowly and get a high yield and equilibrium can be to the right. So that's a higher temperature and higher rate, and this is a lower temperature and it's a lower rate. Okay, so lower temperature and lower rate. Now let's do some simple maths and say, right, okay, if that takes 24 hours and that takes 1 hour, if I did the number 2 for 24 hours and I just took the 10 kilos out and did it again, that would mean 24 times 10 kilos. So in 24 hours, even though I got a lower yield, I would get 240 kilos. So the question is, why do they run the conditions at high temperature even though it gets a low yield? Why do they lower it at lower pressure even though that will get a low yield? Okay, the first reason is all about the rate. So basically what happens is you'll get a lower yield, but you'll get it in a quicker time. So you get as much, and here's the exam answer essentially, you get as much product in the smallest time as possible. Okay, so I'll write that out for you. Okay, you get as much product in as little time as possible. Okay, in as little time as possible. Right. The other one, which they don't tend to ask very much, so I'm not going to write this down, is why don't you have a higher pressure? It's just too expensive. It's just too expensive, so they don't do it. That tends to be an answer on a GCSE one, but on A levels we don't really talk about it too much. And obviously we add the catalyst because we can get everything done much quicker, and that means we expend less energy to make it happen. But the compromise is really important. It's about getting as much product in as little time as possible, because even though we get the lower yield, we get a higher rate of reaction. The final effect we're going to look at is on the equilibrium constant itself. So we've got the equilibrium constant, which is basically products, which is CD, over reactants. So if you think about it in terms of just products over reactants, products divided by reactants. So if the equilibrium yield is towards the right, the number of products is going to go up, which means your numerator is going to go up. And that means if you're having a high amount of products, that your number of reactants will go down. So your denominator will go down, which means that will change the numbers. So think about it in simple terms. Think about it in this way, okay? If you look here, if Kc, and this is only a rough approximation, but it does give you an idea, it has been used in exams. If you've got Kc that's less than 1, it indicates that the equilibrium is to the left. So if it's less than 1. And the reason it is that is because if it's to the left, this is a very big number, and this is a very small number. Small number divided by big number will be a number less than 1. If it is greater than 1, it indicates the equilibrium is to the right. Now, if it's greater than 1, you'll have lots and lots of product, which means the numerator will be very big, and you'll have much less reactants, which means the denominator will be very small. So therefore, Kc will be greater than 1. And this indicates to you, so if you get an equilibrium and you get a number, for example, like 16, so 16 point something, but it says that equilibrium moves way over to the right, and it gives you an idea of the direction and the position of equilibrium.